Hello and welcome. Thank you for joining us for our final webinar in our series, The Hardware Marathon. We have been looking at the phases and some of the obstacles encountered in developing a hardware product from concept all the way through to production. In our series, we've discussed everything from developing a product to protecting intellectual property, to designing a product for manufacturing. And in our last episode, we looked at what's involved in the pilot build for initial production. You can find these on our YouTube channel if you weren't able to join us. In today's webinar, we're going to be discussing the realities of variation in manufacturing. For those who haven't attended the previous webinars, I'm Jenney Loper, the Director of Operations at Zebulon Solutions. I've been in manufacturing since the age of 6, working in my father's machine shop. After completing my degree in physics, I've held positions in every aspect of developing a product, from research to design to testing and scaling production to over 40,000 units per month. Most of my career has been working with a product after it's been designed, and I have over 2 decades of experience in manufacturing quality and supply chain management. In my current role, I have many conversations with people developing their first product, which was the basis for creating this webinar series. Today, I'm joined by Chuck Hodges. He's the CEO and founder of Zebulon Solutions. Chuck, welcome. Would you introduce yourself to our audience?
Thanks, Jenny. Howdy, everybody. So I'm Chuck Hodges. Like many of you, perhaps, I'm a serial entrepreneur. I started out in Silicon Valley, got my MSE from Stanford, did the typical Silicon Valley thing, did startup after startup, ended up doing 5 of them before I got a good exit, a sale to a small contract manufacturer at the time, Flextronics. I was an executive at Flex for over a dozen years, during which we grew 100-fold. So it was a pretty good run. I established their design services group. I set up their global test development group. I ran a plastics factory and worked on a bunch of really groundbreaking products like the Palm Pilot and the Xbox. And like Jenny, I've got scores of product line launches under my belt too.
Well, I'm glad to have you join me and share your experience overseeing a production test and also running the injection molding shop. In our conversation today, we're going to discuss 3 topics: the reality of variation in manufacturing and the creation of defects, the inspection and testing, how to use inspection and testing to capture defects, and then the impact of variation on cost and resources. We would love for our audience to engage with us during the event. If you have any comments or questions, feel free to post them in the LinkedIn window. They will post in LinkedIn, but they'll also show up here in the webinar, and we'll try and address them during our conversation. We will take a pause after each section to address any other questions that may come in, but discussion and together. With that, let's move into our first section, the reality of variation in manufacturing. Most people know that manufacturing makes both good and bad parts, but it's not as commonly understood the connection between process variation and the creation of defects. Now, to be clear, not every variation creates a defective part, but it needs to be accounted for in the design. Essentially, every step in the manufacturing process and every material has variation. And then on the other side, every feature in the product has an acceptable tolerance that works in the product as a whole. Ideally, the variation only creates a tiny number of bad parts. Anything more than this, and it could impact your business, but more on that later. Because we are now talking about a population of parts and not a single piece as we have in many of our webinars, we start using statistics to understand how a product is performing in manufacturing. The reality is manufacturing is about statistics. For the discussion today, we'll assume a well-centered Gaussian distribution around the ideal design dimension, also known as the nominal. That said, actual production may be off-center or weighted to one side or have a long tail. But on the screen, you can see we have 2 distributions representing 2 different products in manufacturing. The right one has more variation in production, and it has a higher standard deviation compared to the one on the left. There could be many reasons for this difference, from the manufacturing process, from what the manufacturing process is capable of, to how the product is designed. Chuck, from your experience, how do you see inexperienced designers typically thinking about manufacturing variation?
Well, it's really too easy these days to think of CAD as truth. If the CAD's right, the part must be right. And that goes up to a point, but it's a bit too naive for reality. In the real world, variation happens. The CAD represents nominal at best, and you get variation from a lot of different aspects of the design, of the manufacturing, of the material supply chain. How much variation depends on many, many factors in the manufacturing process. Automation versus hand assembly is an obvious one. And sidebar, but this is the real value of automation, not the political aspect of labor cost reduction. But automation can be much more accurate. Materials vary, and by materials we can mean everything from steel and plastics to resistors to integrated circuits to valves. Nothing's ever nominal. Environmental conditions while we're doing the manufacturing. Mm-hmm. If you have a factory in Southeast Asia, or honestly in the Southeast United States, in the summer, the humidity is going to be very high. That's going to affect your manufacturing. In the process itself, we have a lot of knobs we can play with for good and for bad, but mostly good in the sense that this is how we control the process. But speed, temperature, if it's a injection molding press, whatever, there's many knobs that we can adjust.
So there's a lot on just maybe material or things like that maybe engineers would think about typically.
Oh, yes.
So the difference between the reality of manufacturing and the design perfect nominal needs to be analyzed to know how much variation the design can tolerate. This is usually represented by an upper and lower bound. So on our graphs, we'll show this with a couple dotted lines. They are placed evenly on either side of the nominal, which may not always be the case, but we're just going to talk about typical today. And so using the CAD, the designers can calculate the allowable amount of variation, either in the electrical or the mechanical design. And these limits are the allowed tolerance. Now, a quick note about setting tolerances. You want to be able to balance accepting the widest tolerance, so things will go together, without compromising on the design integrity, because tight tolerances can lead to higher cost in manufacturing, mostly related to more defect creation, which we'll also talk about later. This applies mechanically for how well the parts will fit together, but also electrically in choosing lower cost components with wider performing tolerance ranges. These tolerances need to be on the drawings for the critical and important dimensions. We don't need to tolerance every single dimension because the CAD does spell out what the part needs to do and what it needs to look like. And so the CAD is truth in that regard, but there has to be some recognize that there's going to be tolerance around every single dimension, even if it's not called out on the drawing. Having the drawing communicates to the manufacturer what is acceptable and what should be rejected. Now, the existence of bad parts doesn't necessarily mean that the manufacturer is bad. It could just mean that the design isn't well suited for the process.
And then there's yield. Love this slide. Okay, so yield, just definition, yield is very simply the percentage of good parts versus the number you actually built. If we build 100 parts and 99 of them are good, it's 99% yield. Yield is never, ever, ever 100%. It can approach 100%. We want it to approach 100%, especially in high volumes, but it's never there. There's always a little bit of red under the curve there. And again, these are ideal Gaussian curves, as Jenney mentioned. In real life, there's outliers that tend to be even further out. So you're always going to have some yield loss. Count on it, plan for it, work really hard to minimize it. That's certainly part of the equation. And of course, understand what you can do at the design end and at the process end to make your yield better.
Thanks, Chuck. So before we move into our next section and talk about how to detect those defects, do we have any questions from our audience about process variation, statistics, or establishing tolerances? And I need to look at a different slide, so bear with the difference of eyes here. Let's see. There is a question here. It says, how do you determine what yield you should expect to have from a process?
That's a giant wild card. It really depends on the type of product you're building and where you are in terms of maturity. If this is a brand new widget that's never been built before, your yield won't be there. This is where experience, though, comes in. And so hopefully you have people on your team and or at your contract manufacturer who've built similar products in the past, and certainly tap into that knowledge base. For electronics products, we used to have a finger in the air rule is that, it should start at, 90 and go up from there. If it was a brand new product, if it was RF, it would start at 80 and go up from there. But that's really, really dependent on the product line. And honestly, if it's a derivative product, it should start at 98.5 and go up from there. If it's something that's really crazy, bleeding edge technology, you might start at 20%. That said, if you're at 20% yield, you're throwing out 4 out of 5 or reworking or other things that has to be factored in. So
one of the projects I worked on, we started at 35%, but we We were trying to incorporate way too many things in a brand new technology, and it was a real
If
challenge.
you're under 80%, if you're under 80% and didn't expect it, you got a problem.
Yes, yes, indeed. All right, let's see. Are there any other questions? I don't see. Oh, one more. How do you know what dimensions should be critical?
You want to take a shot,
I'll take a stab at it. So I think thinking about where the interfacing surfaces are is a good place to start. If you've got a part that has moving components, knowing where those surfaces are going to be interfacing and keeping track of those. Is also understanding in the process what dimensions are likely going to change over the manufacturing time of the tooling or what have you. Those are a couple guidelines. What other thoughts do you have on that?
I think really you have to look at functionality. What matters to functionality? What's going to cause a problem? And if I look at, I'm holding a plastic widget up here that happens to be the speakerphone we're using. The actual dimension of what this curve looked like is aesthetics, but probably not critical, but where it connects together in the back is important. And deep inside this, there's a mounting frame for the actual speaker transducer. And if that isn't with good tolerances, then it's going to rattle. So that's the functionality of a speaker. The functionality of something with a motor in it is very different. The functionality with sensors is very different. The functionality in subsystems have to fit into big systems. So it really takes an understanding of your product and some deep dive into
how things fit together. And,
this is real engineering.
Yes, yes, indeed. Well, thank you for those questions. We're going to go ahead and move on to our next section. We recognize that defects are going to be created, but we want to keep them from getting to the end user or the customer. So how do we capture defects so that they don't get shipped? Now, as a warning, Chuck and I could spend many hours on this subject alone, but we're going to give you a very high-level introduction. If you'd like to pick our brains on this, we'd be happy to meet up over coffee and discuss your current challenges. So let's look at 3 primary ways to capture defective parts produced in manufacturing. We're starting with process controls. Admittedly, process controls is a big umbrella under which you have testing and inspection. It's a general category. It's usually collected from testing and inspection data, as I said. And it's what the supplier or the contract manufacturer will implement to manage their process regardless of the customer. So this is not something you should ask for. This is something the manufacturer should be doing to manage their own processes. The data is usually charted, and they keep a track of where it should be operating nominally, and they will begin to react to it if it starts trending either up or down away from that nominal to adjust something on the production line. It's a feedback loop to know when they need to make changes. They will regularly sample the line. It's really up to them if it's an hourly thing, a daily thing, a weekly thing. It depends on the process and how well it's under control. They'll really only look at maybe 1 or 2 parameters because you just need some kind of a marker that things are starting to go out of whack. And it's really, you wanted to make changes to that manufacturing line before there are any defects being created. One example from my career in the past was I was working at an IC lab, and we had wire bonders. And so every morning the techs would come in and wire up just a few wires, and then we would end up doing a pull test on them to see what the strength was. And we would track that, and if it started to become too weak, we knew we needed to go make some modifications to the wire bonders to bring that back into specification so that none of the little wire bonds that we put in the parts for the day would be faulty, and we wouldn't create any faulty parts. But beyond using inspection to control the process, it can also be used as a gate to capture defects before the product moves to the next step. So it can happen at any time in the process, from receiving and incoming material to make sure that there's no bad material going to the production line, to process controls, as I mentioned, or outgoing as a final check before you ship anything out to the customers. How many parts are inspected? It really depends on the feature and the objective of the inspection. Sampling is most cost effective, but it's not necessarily the most effective in capturing defects. That said, doing 100% inspection can be very labor intensive, and I don't recommend doing that unless it's absolutely necessary due to inadequate process controls. And then there's a couple different types of inspection at a high level. There's visual and measurement. I'll just put those in 2 big buckets. Visual is a very simple pass-fail. It can be automated with a camera system, or you can have trained operators looking for very specific criteria, such as IPC. There can be cosmetic inspections, and those are going to be generally driven by your brand and what the market can accept. On the measurement side of things, there's gauges and kind of quantified measurements. And so gauges such as go, no-go gauges is a simple pass-fail. Those are ideal for production. It's a quick feedback loop on what's good and what's bad, and it can be implemented at 100% or sampled if needed. Quantified measurements, that's usually really only used for initial setup or adjusting equipment in production. It can be used for process controls, but it's not ideal just because it takes more time and it does require more skill by the operators to capture the data. The actual value that you get is not necessarily all that important, but whether or not it just passes or fails. Some tools, you can use either handheld tools or pin gauges. If you're doing a full layout of a part, you might need more extensive equipment than that. So that's kind of a quick overview of inspection, but let me hand this over to Chuck to talk about testing.
Oh, as Jenney alluded to, I could talk about tests for
Yes.
hours and hours, but I don't have hours, so we'll talk fast. All right, let's start back at design. Design drives this. Designing for test, it's actually a thing. It's called DFT. We think about this a lot early on when we're back at step one in those early webinars we talked about when we're designing the product. And what you do at the design level will really impact what you can and can't test. On the types of testing, my general motto is test early, test often. You want to be able to test the product at various steps. Among other things, you want to be able to test it before a bunch of value add into it, labor if you would. But also it's sometimes easier to figure out what's going on in terms of testing when you have a board that we can test versus a big system. When we were doing radio base stations back in my Flextronics days, pretty big complex systems, lots of RF stuff, and we would test these at many different levels, subsystems all the way up to the final system level test. Test starts out with the manufacturing folks, just like what we talked about, process control. They're going to have their own set of, shall we say, manufacturing testing to make sure that they put it together right. If it's a printed circuit board, are the solder joints good? Are they connected in the right ways? Do we not have opens and shorts? Jenney's wire bond example there for integrated circuits, which I've also done too, a whole different world. Then we get to the more functional level testing. Does the widget work the way the widget's supposed to work? If it's a speakerphone, can we hear the noise coming out of it, right? And does it sound good? Subjectively, we might also put an analog instrument on it and quantify this and measure it. Jenney doesn't like me moving around here. Audio system for the webinar here. So parametric testing, which is if you were actually measuring tones, spectrum analyzing, stuff like that, that's a whole nother breed of testing. We try not to do that because that can get very expensive. But for some classes of product, RF being the obvious example, parametric testing is necessary. Destructive testing is sometimes needed. Of course, that has to be sampling. And then there's accelerated testing like HASS, burn-in, run-in, those type of things as well make sense in some circumstances. The purpose for this, really it comes down to money. But money in the very abstract sense in many cases. You have the cost of doing the testing. You can spend 1 minute of labor doing testing. You can spend 50 minutes of labor doing testing. You have the cost of rejects that you throw out. You have the cost of false fails and false positives. That's masterclass level. Rework, test escapes. We're going to talk a little bit more about that. And then more subtly, timely feedback in the process. You want to get the feedback. Process control depends on that feedback coming back very quickly. So you don't want to test a system 6 days after it was built. You want to test it, 60 seconds after it was built so that we don't build more bad ones if there's any issues. And of course, we want to be able to track changes for future revisions.
Yeah, you don't want that big pile of defects to bound up. You want to get that caught as early as possible. Well, before we wrap up this section, we should talk briefly about how defects can escape to the field. So one process kind of related way is tolerances. If I mentioned tight tolerances before, and if you're creating more defects, then you're going to end up with more defects in the field. So tight tolerances can do that. The tolerances can be tight because they're assigned so by the engineer and the process and the product needs it. It could also be that the process itself isn't capable of running well within the tolerances, and so it will just create more defects. it's impossible to inspect every feature of every single product. And so trying to inspect quality into a product is just not a solution. It really needs to be designed into the product and the process. Another way that they get to the field is through inspection errors that can occur because of operator fatigue or operator distraction, or maybe they don't fully understand how to use a tool correctly, so improper training. Or tools could be out of calibration, such as they get dropped on the floor or things like that.
And then on the test equipment side, testers aren't perfect either. Even if it's highly automated, expensive instruments, nothing's perfect. In fact, the more expensive the instrument, the more they're going to come with a calibration certificate telling you exactly what your accuracy and precision, masterclass stuff. We also do some type of tester validation. Typically, when we put production testers out on the line, we use a technique called gauge R&R. Again, very masterclass, but I mean, you want to qualify your test systems as well as your product. But they won't be perfect, and we have to guard band back if we're trying to measure, plus minus 20 microamps, and our tester's only good to plus minus 5 microamps. We may have to guard band that to 15. All right, so complex products are much more difficult. This goes up exponentially, and complex products might just be lots and lots of electronics, or they might be electromechanical systems with fluidics and other technologies involved in them as well. So it all depends on the product. For the more complex the product, more important, back on one of those earlier webinars when we talked about design validation testing, that we do a good job there, because if we do a good job there, we can then do less testing on the actual product.
Right, because during design validation testing, you're looking at all those corner cases. So hopefully when you get to production, you are just testing kind of room temperature nominal.
And it's really tough to do corner case testing.
Yes.
100%, yes.
Well, let's pause here for questions. We've shared a lot of information about inspection and testing, and I'm sure that there's some areas we could probably provide some additional clarity on. Let's see. How do you know if your supplier has process controls or if those process controls are adequate? Go for it.
Okay,
you can start.
I'll start with the first half of the question. How do you know? Is you visit them, either real and virtual, and say, show me your process controls for similar products. And you absolutely ask that question. They won't share, shall we say, the bottom line data of what that other customer's numbers are, but they absolutely should show you and be very proud of. Not only do they have the notebook, they should have the charts posted. Good. I mean, SBC, again, another master class there, but when you walk around the factory, you should absolutely see that on products that are being built today, both posted as physical stuff on the monitors. That's the easy part. I think the second half of the question is
it adequate? It is tougher. Yeah, so when I used to be a supplier quality engineer, I would look at the charts, and then I would look at the charts in detail and really look and see how are they responding to processes when they go out of control. And I actually wanted to see the notebook with all of the previous history to see how often processes were going out of control and what their actions were. And if I started seeing a trend that they were doing the exact same thing and the processes continued to go out of control, then that was a flag that they were probably not making adequate changes or the things were not working well. I'll just put it that way. Another gauge, and there's a lot that can go into this next part, but getting a gauge of how many defective products they have in their defective inventory. Now that can be because they're not designed well and has nothing to do with the process, but you can kind of get an idea if there's a lot of defective product from a lot of different customers, or if it's one particular customer. One particular customer might be a design issue. But
it can be.
They're indicators. I don't say there's no quick rule of thumb on how you're going to know if they're adequate or not. And so,
and if they're not prepared to talk about all this,
that's fair. All right. Well, let's keep going, because I know that we've got more to cover here. So in our last section, we're going to look at some of the impacts of the variation beyond just making defective product. Chuck, this is you.
All right. So let's talk about cost of variation, if you would, here. The most simple one to get your head around is scrap material. If I build 100 units and I have to throw away 5 of them for my 95% yield, that's a cost adder of 5% and change there. That's not always that simple, but I mean, the scrapping the material is the starting point. Remember too, it's not just the materials, it's the value add, all the testing and building and stuff that you've done to get the product to this point also gets thrown out. which is why we come to rework next, because good manufacturing lines, while we try to keep our yields really high, we also try to have rework processes so that we can reclaim some of that scrap material. This is very much a dollar-weighted game. You rework what makes sense. You're putting time and effort into the rework. If you're putting 2 minutes of labor into the rework, you better get a return on investment on those 2 minutes. There's also yield. Not all rework works perfectly. And some rework is much more complex than other. Jenney and I are working with a customer right now who's trying to rework 10,000 units using a laser to cut them open. And there's a reason to do this. It makes sense. It makes cost sense, but of course you don't want to do it. And you absolutely, when you get to that stage, you think about what the money and brand impact and all the other things there, which leads us to field escapes. The real big cost isn't the 1 or 2%. It's if we're having a 20% yield loss, we might have a 2% escape to the field because nothing's perfect. Did I mention testers aren't perfect, Jenney? And so anything getting out to the field is much more expensive. Again, not just the cost of replacing that unit, but the impact on brand. And finally, one of our favorite topics, the impact of inventory and supply chain. This is not necessarily obvious, but if you have a 90% yield, you need 11% more material to build your parts, which we'll get into some other issues in the next slide.
Yeah. Right. And so another impact of poor yield can just be the reduced amount of good product that's produced within the planned time frame. That should be obvious, as it takes as much time to make a good part as a bad part. So you're busy making bad parts, and that's going to take longer to make all the good parts you need. So, and there's 3 options that can happen when you start having a lot of defects being produced, where it's going to take longer than what you expect it to take. So you can ship less product than you were planning on shipping and just short the PO out. That might be the right decision. Maybe maybe you over purchased to cover potential sales that you didn't receive or what have you. You could delay the shipments until the full quantity is made. Customers receive their parts later than expected, and so you might get a brand hit on that. You could also do multiple shipments. Some customers would get their product on time. It does increase your shipping costs, but at least you can keep some customers happier on that. Another way is another additional time is in the overhead associated with managing the defective product. So we've talked about this. You've got to segregate it from good product because you don't want good material and bad material mixed on the line. Otherwise, you can accidentally ship some bad material. You don't want to do that. There's time in reviewing the defective material to determine if it should be reworked or scrapped. If it needs to be reworked, you've got to write up rework procedures and then train your production personnel, and then oversee to make sure that they understood the training and that you're not having yield hit on top of yield hit with the rework. But beyond time, managing defects will require additional resources. We've already talked about the one customer with the laser. One thing, they're having to go out and actually purchase capital equipment in order to do the rework, but it does make sense in this particular case. There's also reporting that's involved in this. So you've got to write the defect up because the person who found the defect is usually not the person to make the decision about what to do with it. And so they need to communicate what they found to the person making the decision. There's reporting around quantifying the costs associated with the defects. So if it's scrap and rework, we've talked about that. One thing on the scrap piece is that there's material and what Chuck mentioned. There can also be recycling and trash costs associated with getting rid of the product. I mentioned this already on the storage side, that you need to have a segregated space, and that can be warehouse cost if you have a lot of material that needs to be reworked or scrapped, and your contract manufacturer may charge you if you're taking up more than what they have allotted you, essentially. And then you have the personnel who need to do failure analysis. I mean, maybe you're getting the defects, but you don't know what the cause of the defects are, and then you need to take time to dig into what the root cause of the failure is. I've worked in many places where they've actually had full-time failure analysis techs just to analyze what the defects were on the line and deal with them.
And then wearing my engineering hat, once we have a defect identified, we need to understand what the impact of that is on our users. Does it mess with our specifications of our product? Are the users going to, in some cases, might not notice the defect? It might be okay. In other cases, this might be really, really bad. And then what can we do to remedy this from the design perspective? And then putting on my management hat, oh, gee, what senior manager doesn't love reading more reports, right? I mean, this is a giant time suck for everything. And the worse the yields are, the the company just grinds to a halt. We've got another customer that their Gen 1 product worked. It got them going. It was literally their minimum viable product, and it worked great, but it had all sorts of field issues, and it just sucked the energy out of their entire management team. When we got Gen 2 up and going, it saved them a bit of money. The yields were better in manufacturing, it was a little cheaper, but the huge thing, which they tell me like every week, it allowed their senior management to go worry about building their business and all the other things that they really wanted to do, which they've been doing.
And I think failing to address those huge field failures that they were having, it could have potentially sunk their business because they were unable to strategize around where the business needed to go. So
yeah, you can get totally obsessed, and correctly. I mean, if you're having a yield crash, you need to focus on it, but there's a big cost.
Well, we've reached the end of the material we had planned to share with you today. We'd love to take some questions on the impacts of variation that you've experienced, or any of the topics that we've discussed today as we finish off our session. I'm going to pause here just to give people a chance to type questions in. If we don't get to your question, we will reach out through LinkedIn, or if you have a specific question about your product, feel free to reach out to us and we'll talk to you about that specific issue. So while we wait, let me just review a few of the insights that we've shared. First of all, yields will never be 100% because manufacturing variation is a reality. When designing a product, consider how the product will be tested in manufacturing to capture those defects. And then when the defects are created, there may be many hidden costs associated with managing them. So let's see. Oh, there's a question on the screen here. Who determines if a product is scrapped or reworked at a manufacturer?
In general, there's guidelines that need to be figured out, especially if it's a CM there. But in general, we want to try to rework everything. And the general rule is if it's going to cost less to rework it than fix it, we want them to throw it out, we do it. So we make that decision there. But this can get complicated, and we can set guidelines for our CMs for the simple stuff, but for complex stuff, there's something called a material review board, which is a giant hair-pulling experience. That for many manufacturing companies meets weekly, and you go through exactly these questions and decide, rework or scrap, rework or scrap. And sometimes the questions can be complicated. That supply chain thing, we need an extra 100 capacitors that we won't be able to put on a board that we're going to ship for production. There's all sorts of secondary costs associated with these things. So yes, and good communications with your manufacturing line, either at your contract manufacturer or if you're an integrated shop between the engineering groups, the business people, the manufacturing people. All these people need to be communicating and making the right decision based on holistic costs, if you will.
Yeah, there's a lot that goes into that. So thank you for that, Chuck. That was a good comprehensive answer to that one. And thank you to everyone else who has joined us today. And we appreciate your participation and your questions. Before we really wrap up, Chuck, is there any insight that you'd like people to walk away with?
I think I'll go back to every time you look at the CAD, and we all do that even at the management level, some engineers spin the CAD for you and stuff. Just remind yourself, it's nominal, it's nominal. And if you do that, it really changes your perspective. And that really helps just thinking of it that way. And then I guess I also will come back to test early, test often. You can't say that enough.
That's right. You get from the beginning of the design all the way through every step of the test, or in a manufacturing. Yes. Well, this does bring us to the end of our Hardware Marathon series. Chuck, thanks so much for joining us today. It was great to have you at the end and at the beginning of this series. So good bookends there. I appreciate that we've talked about some of the hallmarks of steady state production, the manufacturing variation. And while this is the end of the series, be watching for future webinar topics, including the opportunity to ask the expert, some of our engineers around here, just answering your questions. If you aren't on our mailing list for these webinars, drop us a quick note in LinkedIn and we'll work to get you added so you'll be informed when the next one happens. In parallel with the webinar series, we have released blogs on each of the 7 phases. Today's topic is already posted on our website, which is zebulonsolutions.com. And as I mentioned earlier, this video will be up on our YouTube channel. If you'd like to get into contact with either Chuck or myself, please do so on our website on the Contact Us page, or if you'd rather send an email, you can do that at info@zebulonsolutions.com, and just mention the webinar along with your question. Thank you so much for joining us today, and we do hope to see you again next time.